In this lesson, we are going to talk about solving exponential equations. If to refresh your memory, you already know how to solve linear equations or how to solve quadratic equations using quadratic formula. Solving exponential equations is a bit different. The first thing that you have to remember is that if two powers are equal and they have the same base, then automatically the exponents they have to be equal. For instance, in this case, the base is a in both of them, so this means that the exponents they have to be equal. We can use this fact to solve some of the exponential equations if we can express each side of the exponential equation in terms of a base to a power, and hopefully if the bases are the same, then we can say that the exponents they have to be the same. The first example, let's solve 5 exponent 3x equal to 5 exponent 7x minus 2. Since the bases are the same, both of them are 5, we can say the exponents they have to be equal. So 3x has to be equal to 7x minus 2. To solve this one, I'm going to bring negative 2 to the left and 3x to the right. We get 7x minus 3x is 4x is equal to 2. From here I get x is 2 over 4, which is 1 over 2, which is 0.5. That's first type of exponential equations, which is very easy to solve. In the next example, we have 4 exponent t exponent 2 equals 6 minus t. Since the bases are both equal to 4, this means that the exponents have to be equal. So this means t squared has to be equal to 6 minus t. If I move both of them to the left, I get t squared plus t minus 6 is equal to 0. Now, since the coefficient of t squared is 1, I can use sum and product to factor this one out. Find two numbers, product negative 6 and the sum is 1. Those two numbers are 3 and negative 2. So I can write this one as 3 plus 2, 3 minus 2, and t plus 3 is equal to 0. Since the product of two numbers is 0, either or both have to be 0. So I get t minus 2 is equal to 0. So from here I get t is equal to 2, or t plus 3 is equal to 0. So I get t is equal to negative 3. So these are the two solutions here. In the next example, 3 exponent x is equal to 9 exponent x plus 5. If you look at the bases are not the same. But let's try to make the bases the same. I can write 3 exponent x as 3 exponent x the same, but 9 can be written as 3 exponent 2, the whole thing exponent x plus 5. Now distribute x plus 5 into bracket, I get 3 exponent 2 times x plus 5. Now the bases are the same, so the exponents have to be the same. So x has to be equal to 2 times x plus 5, which is going to be 2x plus 10. I move x to the right and 10 to the left. From here I get 2x minus x is x equal to negative 10. In the next example, we have 4 exponent 5 minus 9x equal to 1 over 8 exponent x minus 2. I'm going to write 4 as 2 exponent 2 exponent 5 minus 9x is equal to 1 over 8 exponent 8 exponent x minus 2 can be written as 8 exponent negative x minus 2, which is the same as 2 exponent 3 exponent negative x minus 2, which is 2 exponent negative 3 x minus 2. Now, the left-hand side, if you multiply 2 by the exponent, I get 2 exponent 2 times 5 minus 9x is 2 exponent negative 3 x minus 2. Since now the bases are both 2, I can equate the exponent. So I get 2 times 5 minus 9x is negative 3 times x minus 2. If I distribute 2 inside the bracket and negative 3 inside the bracket, I get 10 minus 18x is negative 3x plus 6. I bring negative 3 to the left and 10 to the right. I get negative 18x plus 3x is negative 15x is equal to negative 10 plus 6 is negative 4. So from here, x is negative 4 over negative 15, which is 4 over 15. So far, we have tried to solve exponential equations when the bases are the same. What if the bases are not the same? For instance, I can give you an exponential equation like 3 exponent x is equal to 5. You can see there is no way I can express 5 as an exponent with base equal to 3. Or I cannot express 3 as a base of equal to 5. How are we going to solve exponential equation of this form? The technique to solve these exponential equations is using the log function. Now, log function has a very interesting property that when it's applied to any exponential function like a exponent b, if you apply log function to this exponent, this causes the exponent to come down and you're going to end up with log a. That's the main property of log function. It will bring the exponent down. So we use this fact to solve exponential equations. Now, remember that this function also works with previous examples, and the result that you get is exactly the same. The first example is 7 exponent x is equal to 9. You can see that I cannot express 7 in terms of an exponent with base 9 or 9 as an exponent with base 7. So the only choice I have is to use the log function. So I'm going to take the log of both sides. So I'm going to get log of 7 exponent x is equal to log 9. Now log 7 exponent x is going to be x log 7 is equal to log 9. Now I'm going to divide both sides by log 7, and I'm going to get x is log 9 over log 7, which is approximately equal to 1.129. The next example, you have 2 exponent 4y plus 1 minus 3 exponent y is equal to 0. To solve this one, I'm going to bring negative 3 exponent y to the right. I get 2 exponent 4y plus 1 is equal to 3 exponent y. I take the log of both sides. I get log of 2 exponent 4y plus 1 is equal to log of 3 exponent y. But the log function is going to bring the exponent down, so I get 4y plus 1 log 2 is equal to y log 3. Now I'm going to distribute log 2 inside. I get 4 log 2 times y plus log 2 is equal to y log 3. I bring y log 3 to the left and log 2 to the right. I get 4 log 2. Remember, this is the coefficient times y minus y log 3 is equal to negative log 2. I factor out y here, so I get y times 4 log 2 minus log 3 is negative log 2, or y is equal to negative log 2 divided by 4 log 2 minus log 3, which is approximately equal to negative 0.4. The next example is e exponent t plus 6 is equal to 2. Just remember that this e here is not a variable, it's a constant in math, which is about 2.718. So to solve this one, again, I'm going to take the log of both sides. So I'm going to get log of e exponent t plus 6 is equal to log 2. The exponent comes down, so I'm going to get t plus 6 log e is equal to log 2. I divide both sides by log e. I get t plus 6 is equal to log 2 divided by log e, or move 6 to the right, I get t is equal to log 2 divided by log e minus 6, which is approximately equal to negative 5.31. The next example is 10 exponent 5 minus x is equal to 8. Again, I'm going to take the log of both sides. I'm going to have log of 10 exponent 5 minus x is log 8. Again, the exponent comes down, so I'm going to get 5 minus x. Log 10 is equal to log 8. But if you use a calculator, you will see that log 10 is going to be equal to 1. So this is 1. So you get 5 minus x is equal to log 8. I move log 8 to the left and negative x to the right. I get x is 5 minus log 8, which is approximately equal to 4.09. The next example, we have to solve 5e exponent 2x plus 4 minus 8 is equal to 0. Again, e here is not a variable, it's the constant 2.7. So I'm going to move negative 8 to the right. I get 5e exponent 2x plus 4 is equal to 8. I'm going to divide both sides by 5. I'm going to get e exponent 2x plus 4 is equal to 8 over 5. Now I'm going to take the log of both sides. Again, the exponent comes down, so I'm going to write 2x plus 4 times log of e is log of 8 over 5. Now I'm going to divide by log e. So I get 2x plus 4 is equal to log 8 over 5 over log e. From here I move 4 to the right, so I get 2x is equal to log 8 over 5 divided by log e. Now divide by 2, and this one divided by 2, so the answer becomes x is log 8 over 5 divided by 2 log e, which is approximately equal to 0.24.